the Precision Farming Conference in Sioux Falls this year? Tom Dorgy was a keynote speaker. Anyway, he's speaking at John Deere, and as I was talking to Tom about that, he said, yeah, he said, I agree with you. I have the same concerns that you have. I don't believe that either. He said, but in fact, what we're going to do, we've got approval to do a project within Pioneer, and what they did is Tom went to his agronomist from New York to California, from Canada to Texas, and told his field agronomist, what I want you to do is go out there and find a farmer that in fact has relatively older planting equipment, but is totally committed to taking that planting equipment to the field this next year. The second thing, the requirement that he'd have is that planting equipment would have to be twice the width of his combine. In other words, if he had an 8-row planter, he had a 4-row combine. If he had a 12-row planter, he had a 6-row combine. If he had a 16-row planter, he had an 8-row combine. You see what I'm talking about, and make it clear. And so many of his agronomists went out and found producers that fit that criteria. Then what they did is said, such a deal we got for you. Since you've already said you're just going to take this planter to the field as it is next year, it's ready to go, what we want to do is we want to bring in a top-level, world-class planter mechanic to go through your planter. But he only gets to go through half the planter. And we're going to leave the other planter, the other part of the planter, just the way it is. I'm going to refer to these as the old planter and the new planter, even though they're the same planter. When I say old and new, you're going to know what I'm talking about, okay? The old planter and the new planter. And so Tom went out and he had his field agronomist go back out to the field and convince the producers that that's what was going to happen. And a very, very large number of them agreed to participate in this program. Tom sent the top level, just a top-notch planter mechanic out to the field to start working on these planters, but they made a terrible, terrible mistake when they did this. One of the things that they did is when they went out to the field, they allowed the farmers to watch the planter mechanic work. Well, the planter mechanic goes in there, and the planter mechanic, you got to understand, comes onto the farm with a semi full of planter parts, all of which were bought and paid for by Pioneer as part of this project they were going to do. And they go in and start working on the planter, and the planter mechanic would take a part, throw it away, put a brand new one on, and the farmer would say, "What's wrong with that?" And the planter mechanic would point it out and show to him what was wrong with it. And when many of them got done with the planter, here over in the corner was just a pile of junk that in fact were broken and no good parts. And by virtue of the fact that the farmer was sitting watching what was going on, about 30% of them said, "Look, I just want to pay for what you've done, and I want you to fix the rest of the planter." ruin the experiment. Anyway, that's what happened. But in fact, about 60% of them went ahead and agreed to do the project. So across America, they had these large number of planters, half of which were new and half of which were old. And farmers took it out, and obviously most of the farmers that they were working with had from between 500 to 1,000 acres that we're working with. So they went out and planted their corn that spring and got everything in the ground, and just about that time of about summertime, as soon as it came out, Pioneer hired a bunch of student agronomists to go out there, and they told the student agronomist, you take this tape measure and you go out there in pairs and you lay this sucker down on the ground, and you lay it right next to those corn plants, and then one of you walk along, and at this point, maybe a 3, maybe a 7, maybe a 13. The one of them would read the numbers off where the corn plant was, right adjacent to the tape measure. The other one would write it down. And they did this for hours out there in the field. And so you can see what in fact they created. They created an incredible data set that in fact showed and described what was going on between the new planter and the old planter as far as planter spacing was concerned. And they did this all across the country. They have that documented, and the students went out there and put this on paper, so in fact they had data sets that in fact showed exactly what was going on. Next thing they did, and as Tom was looking for what in fact he's going to use for a statistic to analyze this with, and actually I talked with him on several occasions about this process. It was decided in the end that in fact he would use standard deviation, mainly because it's a very, very simple number. Who knows what standard deviation means? That's what I thought. Let me go through in this process. If I had a plant at 7 inches, 14 inches, 21 inches, 28 inches, every 7 inches, and it would be perfect, what would be the standard deviation of the plant spacing in that? 0. Okay? Let's go do this again. I got a plant at 6 inches, the next one 8 inches apart, the next inch 6 inches apart, 8 inches apart, 6 inches apart, 8 inches apart, 6 inches. You see what I'm saying? What was the average? What was the average?
7.
7. What was the standard deviation?
2, 1.
It's 1. The deviation from the mean. The deviation from the mean. Okay? We calculated the mean. We determined the deviation from it. Let's do it one more time. 5 inches, 9 inches. 5, 9. 5, 9. 5, 9. What was the average? 7. What was the standard deviation? 2. You guys now know what standard deviation is. You understand that very, very clearly. And you can see that in fact, perfect 0 standard deviation was perfect planted. And you can see that a 2-inch standard deviation was not very good. And you know exactly what that is. You now understand the term standard deviation. It's so simple and so easy, and it's used, and this is a statistic we're going to use. Now the only difference we're going to use is it's a little more complicated mathematically. Theoretically, what we're going to do is exactly what we just did. But mathematically, when in fact we have variable spacing, and that's what we have out in the cornfield, it's a little more complex. Does that make sense to you? But it is the same thing. And if we had a standard deviation of 2, it would be like 5, 9, 5, 9, 5, 9. Okay, are we good with this now? And you can see what we're dealing. So now we have those standard deviations that are calculated for the old and the new, or the new and the old. We have a standard deviation associated. In fact, we have multiple replications done within every field, and we had multiple replications done across fields across the United States. This is really a great data set, and you can see how neat it is to have a data set like that, where in fact you have that all the way around the country. These are real farm fields. But that doesn't answer the question. That doesn't tell us where we're going. At the end of the year, Tom sent out a same group of people, and they said, take the weigh wagon out there, and first of all, you combine down and back where the new planter was. You go right adjacent to that, down and back where the old planter was. Make perfectly good sense? And we document the yield. And we document the yield of the new planter, and we document the yield of the old planter. Let's talk about the results of that. After they've gotten back, they found at that period of time, the new planter typically had standard deviations of 2 to 2.5 inches, 2 to 2.5 inches. The old planter had standard deviations any place from 2.5 down to 8 or 9 inches of standard deviation. Huge differences. And in fact, what they did was looked at the difference and analyzed the difference in standard deviation against the difference in yield. And what they found was that an inch of standard deviation above that 2.5 or 2 to 2.5 typically resulted in 4 bushels per acre of yield loss. That's a really, really, really good data set. That's very, very important and very, very significant. Now, typically it costs about $100 a planting unit to have that planter mechanic to go through that. A 12-row planter, how much does it cost?
$1,200.
$1,200. I take that $1,200, and every time I talk about a capital piece of equipment, a piece of machinery, I want to annualize and acreize my cost. So in fact, I typically use, for my depreciation rate on these planter parts, someplace around 25 to 33%. Why would I do that?
For your life.
I'm going to go through it at least every 3 or 4 years. 33, 25. Do you see that? So that's going to be the life expectancy of this. I'm going to go through this thing again at the end of 3 to 4 years. If you're going to do it every 2 years, what would you use for a depreciation rate? 50%. Okay. All right. So and let's assume an interest rate of about 5%. So in fact, for simplicity's sake, we know that in fact we have a interest plus depreciation rate, and that's what you do when you take a capital item and you want to annualize it. You look at the interest and depreciation, and we look at, I would say someplace between 30 and 40%. Let's just use 30% for simplicity's sake. What is 30% of $1,200, the cost of fixing the planter?
$360.
About $300. For $400. 30% is $400. If it cost us, if we did it higher at 40%, it would have been a little more than that. But let's just figure $400 to $500. That would be the annual cost for that equipment. If in fact we take that across 1,000 acres, what is the annualized acreized cost?
40 cents.
40 cents. Everybody see that? At the most, 50 to 60 cents. Are you clear with me? 40 to 40 cents, at the most 50 to 60 cents an acre. Now, let's go back, and we had a field over here that I've gone through multiple times, and it's about 3.5. That's a standard deviation. What's the yield loss there? If that would have been a field that we're looking at, what would the yield loss have been? 1 inch of standard deviation? 4 bushel. What's corn yesterday?
7 something.
Pretty close to 8. What's 8 times 4?
32.
32 bucks. This is precision agronomics. We ask, it's costing us $32 in yield loss. Fixing it would have been 40 cents. Anybody interested in taking that one? And yet we have farmers across America that aren't. That's how important planting accuracy is. Does that make sense to you? Very, 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 very good sense, doesn't it? And that's where what we need to be doing. I'm not going to have you check there in the book that you're going to get. There's a cookbook on doing standard deviation. I would like on a continuous basis to do standard deviation. When you do standard deviation, you got to understand that from a central singulation unit, the outside row units are going to have greater singulation unit, or greater standard deviations than the middle units. That's because the longer it takes and the more time it sends in traffic through the tubes, the greater will be the variability in the planting. Does that make sense to you? The tubes are a significant part of the inaccuracy that's occurring. It's not just the singulation units. It's the entire system that, in fact, is necessary. A couple of years ago, one of my students gave me a call and said, I want you to come out and look at a field. And he knew as soon as I got there, the first thing I do is I walk through the field, and this is an incredibly accurate field. I couldn't figure out what's going on. So if it's incredibly good or it's incredibly bad, the very, very first thing I do is get my tape measure out and go and find out just exactly what it was. I couldn't believe how accurate the singulation of this field was. I go through, and I had less than 1 inch of standard deviation. I thought I was getting hornswoggled. I couldn't figure out how he in fact did it. We had a good discussion, and he said, "What did you think of my planting job?" I said, "What did you do?" He started chuckling, and he said, "I can't believe how good it is either." He said, he's one of the first around here to start using precision planting units, and they increased the accuracy. Our major machinery companies who weren't interested in planting accuracy in the past all of a sudden became incredibly interested, and that's a great thing. I had talked to machinery people before, and I said, "Why can't we get better than this?" And now that precision planting is out there, competition is great. It's just a great thing for it, and we're improving that planting. So in fact, as a scout, when you walk through the field, you're going to get used to walking through a field and looking for planting accuracy. If in fact it's good, it's perfect, it's great, and you just forget about it and you're done. If in fact you're concerned about it and you think it's not as perfect as you'd like, you go out there and you put a tape down there and you start collecting the data. And then in fact what you can do is discuss the actual data that you have with producers. I think it's a you're not going to gain anything by saying your planter's not working very good. No, you don't want to do that. You want to go out and say that in fact your standard deviation is about 4 inches. Our expectation of good planters would be someplace less than 2.5 to 2, and we need to get that thing fixed. We're losing probably about a bushel an acre, or excuse me, about 4 bushel per acre because of your lack of accuracy. So that's expensive. You can go back through the same analysis we did, where in fact it's going to cost you 40-50 cents to fix it. It's going to cost you someplace in the neighborhood of $30-40 if you're going to lose the accuracy. So that's a very, very important scouting program. Next one I want to talk about is yield estimation through the field. As I talk about yield estimation through the field, this is something I never walk into a field without estimating yield. I'm always out there doing it. The very, very first thing I want you to do is go in, and I'll walk out in a field, and I won't have anything with me, and I'll mark like that, and then I usually start with my toe right at the mark. I end with my heel. Let's see how good a job I did, Kurt.
All right. Got it?
Yep, right there.
17.7.
A thousandth of an acre is what? 17.5. Not a bad job, did I? For purposes of scouting, for getting a good idea, when you develop that skill that you can mark off a thousandth of an acre just like I did, that fast and that easy, and know exactly how to do it, you can walk into any field and you will know the planting population just like that before anybody else will. I typically, after I've done that, I will typically have a discussion with the farmer and ask him what he planted, and if in fact he got close to it, I forget it. If in fact he's a long ways off, I say, let's go out and take a tape measure and see what you really got. And then he can check and see. And so if in fact he's got a significant error out there, it's as much his calculation as yours, and you don't have to defend your estimate. I always go out there with a tape measure, measure off 17.5, and have him count the plants. And when he comes up with 23 or 24, 4 times in a row, you say that's a thousandth of acre. You know that's 23,000, 24,000, the like. Very, very fast and very, very, very effective way of doing it. The next thing I do at this time of the year is I go back to my lines and I count the number of average size ears. What is an average size ear when you go through there? In this time, this year, this is really, really, really hard to pick out an average size ear. You're going to find incredible variability as you go walking across the field. But try to do a good job of selecting the average size ear. You don't count nubbins. Leave them alone. Forget about them. If there are nubbins in there that are just pass them by. They didn't count. So in fact, we had planting population. We knew what it is. Now we have ear population. The next part of going through there with ear population is we want to know how big those ears are. So you know that average size the ear that I have that I've selected, I pull that thing out. What I typically do is put my finger right on top of one of the rows there, and I go 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. This says 18. That's hard to believe. That sucker's 18, but it's got 18 on it. And so I know the number of rows it has, and I put my fingers usually about right here, and I'll go. And this one has got some bad spots on it, so I'll go up there a ways to compensate for the fact that it's got some bad spots. So I'll start about right there. And this is just art. This is not science. I'm just guessing where to start with. But I go from there and I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And I got 19 or 20 kernels. So I got an 18 by 20, and that gives me, put the calculations, a little less than 400. And if I had 27 or 28,000, I have a chart, and this chart is in your handout. There's a chart that both has rows and kernels per row that'll take you to the total, and there's a chart that'll take you from that 400 to 26, 27, about 97 bushel per acre is what in fact I get. That was based upon 90,000 kernels. There's an error in that, and this year I'd be using probably 110, maybe 120, something like that. At least if it's not going to rain anymore, I'm counting on much smaller kernel size than normal. And you say, how do I adjust that? Well, big kernels, what's a bag of seed corn?
80,000 pounds.
Why do we have 80,000? Because into the east, 80,000 was a bushel. For us, 90,000 is closer to the truth most of the time, but in years like this, I think it's going to be much smaller. And so for us, you probably should adjust that down about 10%, and I would end up with an estimate in that field that I've looked at someplace between 80 and 90 bushel per acre. And that was actually, you're going to be able to do that. I'm going to ask you to do that later on and get an estimate, and we'll go around the room and see what you ended up with. But we're going to go in that cornfield right over there and do that. Soybeans. Soybeans are incredibly difficult to estimate yield. I hate doing soybeans. I don't want anybody to ask me to estimate them, and I don't feel comfortable with them because most of the time I'm wrong. And I've done it lots and lots of times and not been very, very accurate at it. I'll pull the stem out, or pull the plant out by the roots, and I'll start and I'll count pods. And at this stage in the gauge, all I do is count pods. When it's close to maturity, I actually and physically count beans and pull them off and count beans. But right now, you get down to these littler ones down here, you can't tell how many beans are in that pod. So right now you just have to count pods and count them down here. And the other thing you got to be very, very careful about is at this time of the year you got something going on. What is this guy right here? This one right here.
Flowering.
He's a future pod, isn't he? You know, these guys are going to continue to make pods and continue to put pods on. So if you do a yield estimate right here, you know that you're going to underestimate it because, in fact, you're at a point where, in fact, this guy is going to continue to add. Unlike corn, where, in fact, you got the number of kernels already determined at this time of the year, soybeans is not. So, in fact, you can go through and use that and I have charts to convert your beans per plant. I should have put in mention. When I talk about bean populations, I want to count those bean populations at a week or two after emergence. To count bean populations right now, you have to get down on your hands and knees and do it. And I hate that. I don't like to count bean population right now. It's almost impossible. You got to go down there and see, and you can't sort them out from up above. At least I can't. And I've tried to do it multiple times. And at one time I had a bet with a graduate student that I could do it from up above, and so I did it both ways and wasn't even close. He got the ice cream. What can I say? Anyway, bean yield estimation is a little more difficult than corn is. Any questions about estimating yields you go through the field? We're going to give you a chance to estimate corn yield over there in that field in a little while. Next thing I want to talk about, incredibly important part of agronomic production, is making certain that we get everything that we need to in the bin, and a detriment to that is harvest loss. And I got a cornfield out there, and a bunch of 1 foot squares that in fact I use. How many square feet are there in an acre?
43,560.
How about I round that up to 45,000, okay? What's 2 times 45,000?
90.
What is it?
90.
90,000. What did I say I was going to use for a count for corn?
90,000.
90,000. So what did we just say?
1 bushel.
2 kernels of corn per square foot is a bushel per acre. Remember that? Pretty simple, isn't it? And so what I do, and I always do this in the fall, is I take this thing out and whenever I'm walking in the field, toss it out onto the ground and count kernels out there, and divide it by 2, and that will give me bushels per acre of yield loss out in the field. Brand new, great combines, somewhat less than a half bushel per acre. 3 places where I can lose yield. First place, critter loss out in the field. Coons, deer, whatever. Not much we can do about that. But in fact, we as professional agronomists got to know if there's loss out in the field. Second loss, header loss. Third loss, separator loss. All 3 are very, very important, and all 3 we need to know. What I typically like to do is go in, if I have a significant amount of loss in the field, first step, determine whether or not it was pre-harvest loss, and if it was critter loss. Second thing, if it's not already out there in the field, I take the combine into the corn, pull the hydrostat back up, and check underneath the header and see what's there. That tells me header loss. The rest will in fact be separator loss. Pretty simple, isn't it? I use typically 2 kernels of corn per square foot, a bushel per acre. I typically will walk down a row, and this varies appreciably, but I've been using about 150 foot. If I find one ear that in fact was a header loss, and 150 foot, that's pretty close to a bushel per acre between a row. Don't go jumping over to the next row. You got to stay within those 30 inches. Okay? Stay within the 30 inches and go about 150 feet, one ear. This varies greatly. One of the real problems I have is that with the variability, it's very common for the little ears to be the ones that are thrown. And if you go looking through a field and find out what's on the ground, you'll find quite frequently it's the little ears. And so that's a real problem. That screws up my calculations a little bit, but I still think it's, if you find an ear in 150 foot, a coarse rule of thumb, you lost a bushel per acre. If you find 2 bushels per acre. Any question about that? Pretty simple, isn't it? As a rule of thumb, and you can verify this, and you'll verify this a little bit later on. I'm going to have you to calibrate your feet. As a rule of thumb, a long step is about 3 foot for typical people. So in fact, 150 foot would be 50 steps. down a cornfield. Now, it's incredibly hard in a cornfield to be accurate with that, but you just do the best you can, and you're getting a ballpark number. Soybeans. Soybean seed size varies incredibly. And this year I think we're going to have quite small. My gut feeling is to use 6 beans per square foot, bushel per acre. I have seen 7, 8, and 9. I've seen them down to as little as 3. We're trying to, in the agronomy club, going to make some little wooden blocks with holes in them. If the bean fits through that, you'll know what size it is. And I think that'll be very, very useful. I'm trying to get that done and working on a prototype at my home right now and try to get the agronomy club to market those. What they really need to do is get an order from somebody like the wheat growers for 5 or 600. Well, who might be able to do that for me? I don't know. Sorry, Brad.
I deserve it, yeah.
I'm sorry. Anyway, typically, the other major loss and the loss that we're going to find this year as we go through the field, our beans are going to be relatively close to the ground. That's a real problem. It's an incredible problem when you got beans close to the ground. I always measure off 4 feet of row, and I count the beans in 4 feet of row. Why do I use 4 feet of row? How wide's the row now? 30 inches? How many feet is that? 2.5? What's 2.5 times 4?
10.
10. What's magic about 10, guys? If I had 6 beans per square foot, was a bushel per acre, and I had 60 beans per 10 square foot, same thing. You measure off 4 feet a row, divide that number by 10, you got the same yield loss. Everybody see that? Is that clear? Pretty simple process. You will know as you walk out in the field precisely what your yield losses are. All this stuff is in the book that I've given you, and be useful for your scouting purposes. What I'd like to do is I'd like to, first of all, I want anybody that's going to get dehydrated on me. There's a bucket full of water over there. I want to make certain you get a thing of water. Everybody drink up. The last thing I need to do is somebody collapsing out here because of heat, although it's not that bad today.
Do you have anything in there on ear size and deck plate settings?
No, I do not. But in fact, that's incredibly important. I leave that up to your operator's manual and the John Deere. But I want you to know afterwards what, in fact, that's really, really, really important, and that's really significant. And exactly where you put your stripper bars is incredibly important. If you have header losses and it's shelled header losses, make certain that you spend time talking with your implement dealer and talking about what in fact they recommend to minimize those. A very, very important part of that discussion is the fact that the drier your corn is, the more yield loss you can expect. And there's an equilibrium that needs to be done with that kind of stuff. Everybody else get water if you need it. What I'd like to do is a bunch of things. First of all, at the tape measure you can see it over there, those 2 ears of corn are located 17.5 feet apart. Calibrate your step. I'd like you to be to the point where you could walk into a field just like I do and feel comfortable and confident that you're marking off a thousandth of an acre just by steps. It's a pain in the neck to take a tape out there all the time, and so if you can become close enough or good enough with that, with your step, you can get an estimate of the plant population. If you're a seed dealer, you definitively want to be able to do that and do that well.
If you look over here at this corn here where you guys were in taking yield and stand count, this was planted the second week in April. This field was planted the first week in May. This is a 110-day hybrid, so it is a longer maturity hybrid. This is multiple hybrids. This field right here has been corn on corn, or in a corn soybean rotation, excuse me. In 2011, it was corn. So this is the second year of corn. If you look at the first page that I gave you, it kind of gives you a little bit of background on the field over on the side here. It's about 15 acres. We took a composite soil test of this 15.5 acres. Came up with 34 pounds nitrate nitrogen across the whole field, and about 8 part per million Olsen P. Average yield came out for the whole field to be about 165 bushel. We used that as a yield goal. And we applied 3 treatments. Single rate fertilizer across the field, a variable rate nitrogen, and then we injected swine manure. Now we put down 8,800 gallons of swine manure, injected about 6-8 inches below the surface. That's a lot. We ended up with right around 250 pounds of available N for this year, if you consider the organic N and the inorganic N that was in this manure. So we juiced her up pretty good. Now, this first page also shows an average yield map for those 3 years of corn that we had. If you look right in the center, we've got pretty nice yields. 150, 175 average. There's these red areas that's right down here. We got a little salt problem. These salt problems also are down in the valleys down on the other end of the field, and they kind of run right in through here too. Kind of miss those. A little edge right here on this corner. But for the most part, we're going to see our high yielding corn right in the center of the field. So what we did is we used just a composite sample. Used our standard 1.2 pounds of N per bushel yield goal, and we used our average yields across the field in a 30-foot grid to come up with a variable rate N recommendation. That's on your second page here. Okay, lower the yield, lower the N recommendation. We ranged all the way from 10 pounds to the acre to 225 pounds to the acre across the field. You can see where we're putting most of our N right in the center, where we're seeing those high yielding areas. The next page gives you a layout of how we did this. We randomized this across the field, 4 replications, single rate, variable rate, and then our manure treatments were only 20 foot wide. The next page gives you how we actually set up our controller files for the applicator. Okay, here you see our variable rate showing up in those variable rate plots. Single rate, we applied 165 pounds of N for this field, right across the field. Our variable rate, again, 10 to 225. Next page shows us what we got. After he was done in the field, applying our fertilizer from our prescription files, from our controller files, we got an as-applied map. So if we look at our single rate, it ranged all the way from 88 up to 211. but most of it was right in that green area there of 151 to 180, which is about plus or minus 10%. Okay, not too bad. Most of the error that you see is on the ends. I mean, he had to turn around, he had to come to the end, he had to slow down, he had to bring that equipment up to speed. You know, that's where the error is going to come in. Except this last plot, and I ain't sure what happened there yet. I was out here when he did this. We had it flagged, and you know, the auto steer and the GPS was working perfectly. He should have put it right where it went, but if something happened with the controllers, I'm not sure. The variable rate, again, we went from 80 to 227, okay? We look at our variable rate plots, we're seeing those high yielding areas getting most of the nitrogen, that 197 to 227, okay? So now let's compare what we prescribed versus what we actually got. Again, if we look at, let's look at our variable rate here first. We were within 25 pounds on our variable rate plots, except on the ends. You know, again, you got to slow it, you got to turn around. That's just how it is. On our single rate, we were within 15 pounds, except that last plot, where we went over by as much as 45 pounds. Now this is real. This is what would happen in an actual field. So we make our prescription, we say, okay, we're going to apply our fertilizer variable rate. How close are we actually hitting it? Okay, that's one thing that we set out to do with this. The other thing that we set out to do with this is to demonstrate differences between a single rate applied fertilizer and a variable rate applied fertilizer. And can we do it from one composite sample in the field, or one composite sample in a management zone, as opposed to grid sampling, which is a lot more expensive and it's labor intensive. The manure is kind of a separate thing, but I was really interested how it was going to turn out. I pulled some ears. You know that high yielding area out in the middle of the field? There they are, guys. That's what I'm going to get. Kind of that in between average to high yielding areas. That's what I'm going to get. And those low yielding areas, yeah, not a lot there this year. Mother Nature has a way of sneaking up behind you and kind of derailing things every so often, and that's kind of what happened this year. Now there's a few things that we can learn from this, though. You know, he's got to make lemonade out of lemons, right? One thing about a dry year is you can pick out those poorer areas in the field real easy. And if you can mark them, you can get out there and map those. You can go back to them and find out, what can I do to improve those areas? You know, is it a drainage problem? You know, maybe it's an eroded hilltop, it just lacks organic matter. Maybe I can try to increase my residue. Maybe it's a saline problem, a salt problem. Salt problems are, you know, the one thing about salt problems is after a dry year and we start getting rain again, he'll move that back down. Right out on this mile road here, you'll see a large area. Well, I've been down at the Beersford farm off and on, time to time, for the past 20 years, and I remember that area. Was no bigger than the area of this tent. Now it's close to an acre. Nothing's growing there. So the past few years we've seen a lot of water. Somebody mentioned a couple of years ago we had the wettest June on record. Okay, that's raising that water table, bringing those salts up. We're starting to see those saline areas pop up. We're seeing it in this field. The other thing we can learn from a dry year, or well, let me back up here. If you had a farmer, you were working with one of your producers, and he says, I don't want to sample for nitrogen this year. Next year. Just don't want to pay for it. What would you advise him after a year like this? Do we know how much N this crop is going to use? We fertilized for an optimal crop. Okay. How much residual N is going to be out there next year? Lots. Okay, so unless I'm going into soybeans, which will suck up a lot of that residual N, I probably need to sample that. With this study, we'll probably need to grid sample this. We don't know. But after a crop failure, there's a good chance that there's going to be a lot of residual N there if you fertilized. So in a continuous corn system, it's real important to, after a dry year or a crop failure, you want to get out there and pull those samples. That's what I have. Any questions, comments?
What's the difference of cropping on these two sides? I mean, when you got those kind of years and that just across here?
Well, a lot of this is differences in variety and differences, yeah, you know, and planting date. I mean, I'm not ready to say, you know, this is proof positive that planting date is going to make a difference, but, you know.
It seems to be, sure.
Yeah, well, I think there was some drought avoidance there. We had some rains early on this year where the plant was able to get established where, you know, and this is just a difference of about 3 weeks.
So you don't put any phosphorus on these plots at all?
We did. Well, okay. Tell you what we did is we applied 60 pounds of P2O5 over the whole field.
60 pounds, okay.
Okay. 60 pounds, excuse me. And theoretically, that equalized the P. Realistically, did that equalize the phosphorus in this field? Absolutely not. Because phosphorus is so variable, but I applied the same amount, but we assume that our soil test is telling us this is how much phosphorus there is, and we should fertilize accordingly.
Do you know what your zinc levels were in these soils?
No, we didn't take samples for zinc.
How come?
Never seen any zinc deficiency.
It's all been above 1 part per million.
Pretty much. I mean, I remember Ron has taken samples out here, and some of them came back like 3, 4, 5, if memory recalls. But I take that back. I have seen zinc deficiency out here, but usually it's been like real early in the season, and it's usually brought on by climate, and then the plant grows out of it.
Did you do any like tissue tests, like at all during season?
No. At this particular point in time, a tissue analysis really doesn't tell us a whole lot. It doesn't give us any information as far as, I mean, what do we use that data for? Because it's so variable, and we haven't seen that correlated back to yield. Or are we able to use that data to make fertilizer recommendations?
Somebody the other day told me that tissue testing tells you whether or not you need to do a better job with your soil testing.
You know, the corn stalk tests that they did in Nebraska and Iowa, okay, they don't do that anymore in Iowa. Okay, Antonio Malorino was the one that first came out with that. If you look at Iowa's nitrogen recommendations now, there's 3 zones for corn. If you live in this zone, it's this much, and it's a range. If you live in this zone, it's this much, and it's a range. In this zone, it's this much, and it's a range. Used to be a yield goal-based recommendation system. Used to have the corn stalk test. Don't do that anymore. How come? Because when they went back and did the work, and they tried to correlate those yields back to the recommendations with what they were using, they found that they were not correlated. So they pulled the corn stalk test, and they pulled the yield goal recommendation and went to a zonal nitrogen recommendation schedule. And it's up to you guys, the agronomists, to help that farmer set those rates so that he's going to realize optimal profitability. North Dakota has done the same thing. They're redoing their recommendations right now. Dave Franson, did he come out with the wheat recommendations yet, Greg?
I haven't seen it.
Okay.
So they don't even recommend soil testing in Iowa?
Oh yeah, they do. I mean, it's based on a soil test, and then there's a range of fertilizer rates that they give you according to the soil test.
Oh, gotcha.
When I talk about precision farming, and I spend a lot of time discussing that, one of the things that I always say is that we have to start out with very, very good conventional farming. And from my perspective, that in fact, before we start precision farming, you need to have impeccable agronomics that in fact are what we call conventional agronomics. When I talk about that, I first start out with seed selection. Seed selection is something that in fact just drives me crazy. When I was growing up in Illinois, my uncle was a DeKalb dealer, and I used to travel around with DeKalb with him when he made calls and when he made sales, and we'd go into a farmer's office and we'd spend someplace in the neighborhood of 10 to 15 minutes in there getting a order, which in fact was just a short discussion about different varieties. It wasn't much of any discussion whatsoever. From my perspective, I believe that there's at least a 10 bushel per acre differential between the people that make top variety selections and those that make mediocre variety selections. At least 10. Now let's start thinking about that. 10 right now at $8 is how much per acre? $80. And on 1,000 acres, that's what? $80,000. And I would ask everyone here, how much should you work to earn $80,000?
About a year.
Or more. I mean, that's how important this is, and people don't do it. In academia, we should be doing a great deal more work than we're doing on these. We should have a compilation of every side-by-side variety trial that's conducted in the state, and that should be available for printout. There's just all kinds of stuff that we ought to be doing. Seed selection is incredibly important. Nutrient management, we've discussed that and discussed it to death, and I'm not going to spend any more time talking about it. Appropriate tillage. Appropriate tillage is incredibly important. When I talk about appropriate tillage, one of the things that I've been an advocate much of my life is for no-till. You have to understand that, in fact, the beauty and wonder of no-till is it saves 2 to 3 inches of moisture. You have to understand the curse of no-till is that it saves 2 to 3 inches of moisture. Understand what I just said. The beauty and the curse, and how you manage it and how you live with it and what you do with it. And as I look around, and I'm a believer in cycles, and I'm a believer in looking to the south the year before and seeing what the weather's like and saying this is what's going to happen to our place the next year. So in fact, I looked to Nebraska last summer and saw a drought down there, and I said, we're going to get this sucker. And then spring came, and look how smart I looked. We had nothing but rain. But right now, I'm in hog heaven. I probably would have thought about no-till in the spring, and if I had thought about it, it would have been a train wreck. Because let's be realistic. The problem with no-till is in wet springs, it's cold and wet, and you can't get the stuff in. The beauty of no-till, I started no-till in someplace in the neighborhood 30 years ago. And I started as a university agronomist. And we had a number of fields out there, and I can remember one of the drought years, and it was been in the 80s, one of those drought years. Went out to the field in June, and we'd planted it in May, and went out to the field. And the no-till corn beside the conventional corn was like this, and the conventional corn was like this, and this was night and day. And if you swore about no-till, it was at it. And then in that drought year, we went back and we watched it during the season, and I said later on in July, I said, this corn is still going strong, while the conventional corn was just looking like this. Then we went back to harvest, 70 bushels for the no-till, about 20 for the conventional. 2 to 3 inches, huge differences. That's what it did. That's what it's about. Managing that is incredibly, incredibly difficult. You got to be knowing, you got to be a prognosticator of what's going to happen with the weather. And obviously, this year I would have been a total, complete failure. How you do it is incredibly difficult. But if you look in the past, wet weather begets wet weather, dry weather begets dry weather. We know that to be the case. We know it takes a while for that buffer to catch up. And so, what are the probabilities of next year being dry? I would say that they're better than 50%. That's what I would suggest. Appropriate tillage. Seed placement, depth, timing, seed soil contact, and accuracy. You got to. I have made the statement time and time again. The most expensive piece of equipment you have on a farm is your planter. And it's the most expensive piece of equipment, whether or not it's worth $100,000 or worth 50. Because if it's worth 50, it'll probably give you a terrible stand. Do you see what I'm saying? The most expensive piece of equipment you got is that planter, seed placement.
Like this year, a lot of our customers had poor stands because of that rain in May.
I know.
So they had like 18,000. So a couple guys replanted like whole quarters.
Yeah. The real beauty is the weatherman knew exactly what was best for them. If they just left it at 15,000, 18,000, they probably would have had better yields than what they got by replanting it.
So now the replanted stuff was, the ears are real short.
Yep. It's late. Whereas we probably would have come out smelling like a rose, but how do we know that? Hindsight's 20/20, ain't it? Isn't it? It's just terrible. Weeds, insect, disease management need to be impeccable and need to be great, and you need to scout. I've made the argument that in fact every farmer needs to be scouting every field and most of the acres every week. And I've been criticized by some of my old students that in fact are top-rated agronomists, and they said I'm wrong. It needs to be done twice a week. And so what can I say? Speaking of weeds, insects, and disease, Kurt, talk a little bit about apps and scouting.
Gregg and I and some others at SDSU were putting together a suite of mobile apps. They'll run on Apple, iOS mobile devices, and Android. The first app that we're coming out with is going to deal with stand count. Okay, now you're going to say there's a bunch of them out there that are stand count calculators, and there are. What makes this unique is it has a Google Earth feature. As you're out in the field and you're doing some of the stuff that Gregg has been talking about, just the real simple easy stuff, I'm taking stand counts. I can now move around in the field and I can record that location where I took that stand count. I can see where I'm at in the field just by looking at my mobile device, and I can move around the field and take a number of samples. Once that's done, I hit export, and it sends me via email a CSV file that can be opened in Excel. It can be imported into GIS systems and used with variable rate planting. How close are we hitting what we're prescribing? How do our stand counts match up? Be used by crop insurance folks to document losses when they're out in the field. Be used by farmer. Be used by anybody that's in the agricultural industry. That's the first of this suite of apps. We have ideas and conception for about 30 of those apps. There is some discussion about getting it on a Windows mobile platform so you can use them within, your Trimble or Magellan units that run on Windows mobile. But as Gregg talks about, weeds, insects, and diseases, these are real threats. Those are real stress threats. So we have mobile apps planned for that, where you can actually scout your fields and record where you see those diseases, where you see those insects, and what the populations are. Now think of the power of the data if we can get enough of those points throughout the state and around the state. We can start to track the movement of invasive species. Maybe track the movement of Roundup Ready weeds. Track the movement of diseases, insects. We're talking about marketing, and that's the next on drying, storage, and marketing. Can I take this 18% corn out of the field and haul it to town, just take the dockage, make more money, as opposed to drying it at home where I'm buying expensive LP gas and the elevator in town is running on natural gas, which is dirt cheap. Which is going to make me the most money. So these are some of the things that we have planned, some of the things that are coming in the future. The first of those apps will be released soon. We're in beta testing right now. And if anybody has an Android device and would be interested in being a beta tester, come talk to me. I'm having a hard time finding Android beta testers. Everybody seems to be moving to Apple. But questions, comments? Does that sound like something that's usable to you guys and interested in?
And something. We talk about drying and storage. Kurt alluded to that. Since we have all this natural gas that's coming online, and natural gas is going down, it's been as low as $2 per million BTUs. When you think about a current gallon of LP, you say it's cheap, 99 cents. It has approximately 92,000 BTUs in that gallon. 92,000, so it's about $11 per million BTUs, as opposed to natural gas at $2, $3, and $4 per million BTUs. I rather suspect that natural gas is going to continue to be that with all the hydraulic fracking and all that's going on, and I think there's going to be a huge differential there. And calculating those differences, that's why in fact in a lot of circumstances it may be less expensive for you to haul grain to Brad over there and to one of your elevators that in fact is running natural gas, as opposed to running it at home running LP. And those are things that people need to be talking about and sorted out and discussing, and doing the calculations of, and some of the things that we're talking about, the apps will do that for you, make that comparison. Do you see what I'm saying? I mean, these are things that, in fact, are management decisions that are incredibly important. I'm going to go on to some precision farming items, and I'm going to look at some maps, and I want you to look down here at 2 precipitation records. This is precipitation from the Opportunity Farm about 10 miles north of here, closer to Lenox. I want you to look at 2007 and 2009. 2007 we got 31 inches of rain. 2009 we got 23 inches of rain. Huge differences in those years. This is yield monitor data from 2007. The red is really low yielding. The orange, the green, and the blue are relatively high yielding over here. Notice how low this part of the field was. These were planted the same hybrid, the same variety, everything. It's just this part of the field is wet. This is 2007, the wet year. Look down here at 2009, the drouthy year. What do you see? Just the opposite happening. The high yielding is over here. The lower yielding, it's still very, very good corn crop over here. It's still pushing over 200 bushel per acre, but this is up there in the 230s and 240s with that drought year and that wet soil that doesn't have a good drainage system in it. And so minimal drainage in here. We're talking about putting more in, but that's in fact just what happened. When I talk about precision agriculture, and I spend most of my time using yield monitor data as my source of information for precision agriculture, one of the things that I want to have is determine, is it high yielding, is it low yielding, and is it high yielding with standard deviations that are low? I want my standard deviations are low, and now that you are experts on standard deviation, you understand what I'm doing. What I'm doing with that. I want to know how it deviated from the mean over years. And in this particular case, if I can have in part of field that in fact is high yielding, low standard deviation, or low yielding and low standard deviation, I can manage those in a precision way. What I can't manage very, very effectively is anything that has high standard deviation associated with it. Because in fact, unless I can prognosticate what in fact is going to happen with the weather, I don't know how to manage that. And that's a very, very difficult thing to do. And those are real problems that precision agronomists are trying to deal with these days. The high yielding and the low yielding parts of the field that are consistent, we can do that. Here you have map. This is an average map from 2006 to 2011. The yellow and the green are low. The bluer portions of it are high yielding. This is a field that went from average, and I talked about this before, that had places that were at 100 bushel per acre average over long periods of time and 200 bushel per acre over long periods of time. That's the kind of thing that we find. It's not atypical of finding that kind of different data and that kind of information in South Dakota. Here is the standard deviation map. This is a map showing that you have the high standard deviations over here and the low standard deviations over there. Actually, they're not standard deviations, it's coefficient variation, which is very, very close to being standard deviation. You can look at the colors. If you just look at the colors, now look at the thing, you are looking at standard deviation. And you see, these are the kind of maps that we create and use, and this is how we manage our precision material. People ask me, what would I use and what would I precision map and what would I precision farm? Number one of all the precision things that works and makes money is liming and pH. Now, we don't have many liming and pH needs except in the fir south and southeastern portion of the state. So over in this part of the state, as we move here and go west, it's not really significant. And as we get into Iowa and Minnesota, if you are liming, you absolutely need to be doing it in a precision way. You need to be grid sampling, and you need to be applying that lime based upon, well, actually, if you want to come right down to it, lime recommendations are precision-made recommendations. They're point recommendations. And so consequently, if you know what, in fact, and grid sample the field, you're in a position to do outstanding management as far as lime is concerned. Next, I would argue my next important variable is phosphorus, and phosphorus is an incredibly important element. I would argue that in fact we've probably, as we've conventionally farmed, we've made some really interesting mistakes that are very beneficial to us. What we've done is uniformly applied phosphorus over the fields, but we've not uniformly mined that phosphorus out. We have high yielding parts of the field and low yielding parts of the field. The high yielding parts of the field take more phosphorus out. I would argue that in fact, if you grid sample, you'll find that your low yielding parts of the field will have higher phosphorus soil tests than the high yielding parts of the field. That's because of non-uniform mining that's occurred and uniform application of phosphorus. And as you look at that and understand that, that's really interesting. I also believe, however, that the low yielding parts of the field need higher levels of soil test phosphorus than the high yielding parts of the field. A number of soil scientists agree with me on that. And so consequently, by mistake, we've done what's right. You know, and what can I say? I'm not going to spend any time on nitrogen. Nitrogen is something that in fact we need to be a little bit cautious of. We find that in low yielding parts of the field, we're optimizing our yield response curves at higher rates of nitrogen per pound per bushel, 1.4, 1.5 in the low yielding parts of the field. As far as the high yielding parts of the field, they might only need 0.7, 0.6 pounds per bushel. And so if you really understand what I just said, it's not very conductive to precision agriculture. It says we're closer to a uniform rate across the entire field of nitrogen. And that's what a number of states are coming to the conclusion of. The big ones for us, number 1 and number 2. We need to be looking at site-specific populations and site-specific varieties. Both those are important. In the next year, next spring, Southeast Farm is going to have a planter that has the capability of putting 2 varieties anywhere where they want, mapping and putting in there. Where it's really significant is in the saline parts of the fields. We need to have a different variety because in fact we can gain appreciably from that. We can gain, the racehorses that we like to put on the good parts of the field are not doing as well in those saline areas. We have some workhorses that we could put out there on those saline areas which could out-yield the racehorses in that particular area. So in fact, and the mapping of that, one of the real problems we have, and I'm trying to get the seed companies, I'm trying to get some of the co-ops to put out variety trials on these saline spots in the state. So in fact we can determine what in fact varieties, both soybeans and corn, are most effective in those particular parts of the field. That's a money maker, and it's not going to cost us that much to do it. Another money, I mean, the truth of the matter is when you really start thinking of the mechanical parts and the software parts of on the go, it's not incredibly expensive to do it. We're talking maybe less than 50 cents an acre to do it. If we can gain a couple bushel per acre, look where we're at. Varieties are well known. You saw the field a little while ago, and that said in some parts of the field we need to be growing. We have an average of 100 bushel per acre. In another part of that same field, you saw we had an average over long periods of time of 200 bushel per acre. In the 100 bushel per acre parts of the field, when I'm growing corn, I'd like to be planting someplace in the neighborhood about 26,000. And in the high yielding parts of the field, I'd like to be planting someplace in the neighborhood of 36,000. Who sold corn lately? Who's bought it lately? Sold or bought? How many dollars a bag, Brad?
I haven't been involved in that, so
$300 a bag.
300, yeah.
Why don't you make it easy for me? Why don't you say either 320 or 320 or 240?
Yeah.
320.
320. Okay. Okay. How much is that? 1,000.
$40.
If it was 240, how much is the 1,000? $3. Dollars per thousand. Is $3. If it at 240 a bag, it's $3. At 320 a bag, it's $4 a thousand. Okay, everybody agrees with that. Now look at that field. No matter what we were doing, if we didn't variable rate across that, at the high yielding, we're off by $40. If we in fact planted at the lowest rate. If we planted at the highest rate, we're back off by $40 in the low yielding parts of the field. You see what I'm saying? No matter where you're doing, you're wrong. That's why we need to be variable rating it, and that's why it's going to be a moneymaker to do it. Not only are you wrong as far as, and I'll talk about what in fact I talk about. When I talk about this, I'm talking about what is the optimum planting population. And the optimum planting population comes from looking at, there are 3 parameters that are necessary when we look at optimum planting population. One of them is the shape of the yield response curve, the second one is the cost of the seed, and the third one is the value of the commodity. Those 3 things. If we have those 3 things, and we can solve the differential equation, which in fact defines the optimum very, very simply down to the nearest cent. Now the problem is when I talk about yield response curve, Mother Nature is always going to do it to me. You know, she's always going to change things on me and give me a hard time. But in hindsight, I can be very, very precise, and I should be able to use that for forward. If you look at this graph down here, we're putting a number of plots out and have a lot of plots that are out there where in fact we go a half mile across the field. This was one for western South Dakota where we went from 12 to 24,000 plants per acre, and we had in high, medium, and low yielding parts of the field, and we developed yield response curves. When I talk about yield response curves, I'm talking about this kind of data, and I have lots of this kind of data. This came from many, many different. This is a yield response curve that was an average for yields where in fact the maximum yield was less than 100 bushel per acre, or about 100 bushel per acre. At 18,000, at 24,000, at 30,000, these are the yields I'm looking at. From 100 to 130 bushel per acre, this yield regime, this is what the shape of the yield response curve looked like. From 130 to 160, this is what the yield response curve looked like. 160 to 200, this is what the yield response curve, and from 200 greater, this is what our yield response curve looked like. These were a very, very, very large number of field trials where in fact we had multiple different populations that we put in there. That makes sense what I did here? The next thing we do is we take that to a computer program and we optimize for each one of these yield response curves what is the most profitable level of seeding to put on based upon an incredible amount of data that we have. And what we have is these blue dots are dots where we made the assumption that we had $6 per bushel corn, $4 per thousand seed. That's why I really wanted you to come up with 320. And the blue dots is the optimum planting population based upon the yield potential at that particular place. Notice at 100 bushel per acre, this curve says that ought to be at 25 or 26,000. Right in this area, right in here is where I ought to be. Notice for 200 bushel, it says I ought to be up at 36,000. I will tweak these based upon the specific variety that I'm dealing with, and I like Pioneer does an incredibly good job of showing us how their specific varieties yield responses behave, and I can put 5,000 or 6,000 on dot either way based upon how the yield response curves look. And but this is how we do it. This is in your handout. The equations down here are the equations that in fact would generate the yield response, or the optimum planting population equation for this particular set of data set. You probably can't, no place else can you find that kind of work done. Very, very powerful, very, very useful. If I look at $2.80 a bag, that's $3.50 per thousand. And at $5, and I talk about, give an example of how in fact we can have the loss or gain from that. Variety selection I talk about down there. We need to be planting these kind of things on and planting different varieties as we go across the field, and we need to get the seed companies to do a good job of determining especially what is good in high saline areas. Now the seed companies already screen for iron chlorosis, And iron chlorosis is not necessarily high salinity. That's a problem, that's a concern. Iron chlorosis typically occurs when you have high pHs, and it results from low nitrogen availability at high pH. It doesn't necessarily have to be high salinity, though sometimes they intertwine with one another. So that's incredibly important that we get that screening done and have more, because we're going to have that capability. I talk about site-specific N, P, and K, but more important, I want to spend some time about precision placement. This is an opportunity that I think is incredibly important. If you notice, and if you look at a soybean root, for the most part, that taproot goes straight down. If you look and see, if I'd put my fertilizer 2 over and 2 down from there, from the year before, a very, very real possibility could miss it. We ought to be putting our fertilizer down below. Now, what's the real problem with that? The problem is we're putting on DAP and MAP, and we're putting it on corn the year before, and in the past we didn't know where that fertilizer was at. With RTK now we have that capability of knowing where that fertilizer is located, and that's a real beautiful opportunity. I would put that fertilizer down deeper in the soil profile, maybe down to 3 or 4 inches, and I would put the soybeans directly over top of it. I'd leave them exactly, I'd put it 2 over and 3 down or 4 down with the corn, and I would put the soybeans over the 2 inches and put them right over the top of that slip. Let the corn take the nitrogen out. Now I got the phosphorus available for the soybeans. I think that's an opportunity we need to be looking at. We're doing some experiments by putting, we're actually using triple super, I keep on getting it backwards, triple super phosphate instead of DAP and MAP, and we're putting it down below the seed during the year. I think that's an opportunity. There's data from the Eastern Corn Belt which would indicate that they have significant yield response occurring by putting those rates directly below the seed. And that's what this one is, 1 inch below the seed. Some pictures of some of the work we have in the lab, where in fact, if you see, we put the phosphorus over to the side, soybean plant goes right down beside it. We put the phosphorus right below the root, it comes down and grabs it. Those are our laboratory studies we're doing. Working pretty good. Another opportunity that I see happening, what time we got?
Oh, you got 20 minutes yet.
I still got, what happened? How did I get that much time? Well, you guys came early, that's what happened.
Oh, there you go.
Yeah. Well, I tell you what, we're a captive audience. No way we're going to get out of here until the bus comes, so we might as well just keep on talking. Why is everybody looking at me nasty like that?
With that 2x3 or 2x4 for fertilizing, you're saying you're going to fertilize for next year's soybeans with the corn that you put down?
Yeah, that's just the way we do it now. That's how we're doing. That's how we're going to do it.
Okay.
And because for our practical purpose, we're getting the nitrogen free from the MAP and DAP, and it's hard to get triple super. Does anybody have stock triple super? Do you guys?
You can't get it.
Well, we can get it for research purposes. We're paying through the.
The unit of phosphorus is about 30 to 50% higher too. No.
Yep, it's terrible. I really don't understand as I look through the manufacturing process why that's the case, but in fact it is. So.
It has to do with the acid, a few other things in manufacturing.
Yeah.
Possibilities.
All they're using is phosphoric acid instead of nitric acid. Why? You know, that's the only thing that's different. But anyway, auto steer is here to stay. The first auto steer I saw was on a producer that I worked with for a number of years. I actually helped him install the auto steer system on his Challenger tractor. He called me up and said to come out and spend some time looking at it. He had a problem. Well, by the time I got there, it was working fine, and he was sitting in the tractor planting with his auto steer running, reading the Wall Street Journal as he drove across the field. Auto steer is here to stay, and we're gonna continue to see auto steer used. I can give you all kinds of examples, but the biggest one is, in my opinion, this fatigue and timeliness. And fatigue and timeliness is worth a significant amount. If you don't believe it, look at that corn compared with this corn. More timely put in, less timely put in, and look at the differences. Maybe there's more to it than that. There's probably the short season and long season populations and some other stuff, but in fact, I think that's part of it. Another area that, in fact, I think has real opportunity that I think we can look at, and something that I found quite disturbing. About 15 or 16 years ago, we started driving across our fields and using Roundup, and one of the first things that was a casualty of Roundup were our waterways. And if you spent time this spring going across to look at fields, it was one of the worst erosion periods that I've seen in years. And it saddens me greatly as a production agronomist, not a tree hugger. Nobody would call him, would accuse me of being that. But in fact, when I see erosion occurring, I see lost productivity. That's what I see. And I think it's incredibly sad. And I think much of the erosion we had resulted from the fact that we were using Roundup. We just sprayed across those fields, and we didn't have an effective way of turning off those sprayer booms. If in fact you went across and turned off those booms and the waterway was at an angle, what you got is a huge weed crop that came up there, and that was unacceptable. And I've seen circumstances where people try to do that. Today, precision agriculture gives us the opportunity to control each individual sprayer outlet by itself as we go across the field and drive that just by a map, and the map will turn it on and turn it off based upon where the waterway is, and we ought to be reestablishing those waterways because we have the precision technology which will allow us to put them in place and keep them there. I think it's a real opportunity. I think we need to be doing that as opposed to losing that potential as we go across the field. I want to go back to something I skipped because I didn't think I had enough time. Talking about yield monitor calibration, because I think that's an incredibly important part of precision agriculture. And we need to make certain that on a continuous basis we're working at doing the yield monitor calibration. Lots of different ways are suggested. Follow the operator's manual. Revisit calibration when you change varieties, species, and moisture content. You got to keep those calibrations up to time. The last thing I want to spend some time talking about is yield monitor cleaning of data. If you understand how a yield monitor works, you can understand why, in fact, almost always there will be garbage in a yield monitor file. Let us make it clear that, in fact, our combine header is picking up the grain, and it's taken any place between 13 and 20 seconds for it to travel through that combine back to the clean grain auger where in fact the mass is measured. Okay, what happens if I do something from a management perspective, i.e. if I stop my combine in that time period? That yield monitor will for a period of time continue to be receiving grain where in fact the velocity of the combine is very slow. The yield monitor is going to think that you have huge yields. That data needs to be cleaned, and it can be cleaned very easily based upon a criteria. When I change the velocity of my combine, I need to clean that data out of there because it's not valid. If I'm running at a constant and continuous speed, the yield monitor will do a very good job of monitoring what's really going on. If I change that speed, it's going to be messed up. And so when what we have is algorithms in this yield monitor. My recommendation, and it's in the notebook, there's a yield monitoring program that's actually freeware that's from the University of Missouri Extension Service. Actually, it's from the ARS in Missouri, the Agriculture Research Service, and it was put together by a bunch of us that in fact worked on that program. It's a freeware program, doesn't cost you anything, you just can load it up and run it, and there are all kinds of filters in there that allow you to clean your data very quickly and very easily and make it into a really good set. At the ends of the fields, it's a problem. When you're starting and stopping, it's a problem. If you stop in the middle of the field, it's a problem. All these things would be cleaned out automatically by the filters in that software package, which will allow you to allow the yield monitor to work as it was intended to work.
Greg, what do you do if you don't have combine velocity? How would you recommend cleaning that data set?
You do have combine velocity because you have GPS locations.
Well, let's say we don't. So somebody gives you a yield monitor data set, we don't have combine velocity.
Do I have latitude and longitude?
Yep.
Well, the latitude and longitude, I can calculate combine velocity, and that's what we do. So it's in there. If I have time and latitude and longitude, I can calculate that with no trouble.
I've gotten yield monitor data, so all I've got is lat, long, and yield. That's it.
You don't have time?
Oh, and I've got garbage data in there. What I've been doing is 2 standard deviations from the mean.
That's part of there's a filter in there to allow you to do that. You know, you can do that and get that stuff out. Hey, you know, obviously when you go and see a yield monitor file and it has 400 bushel per acre and you know you're combining soybeans, you know something's wrong. But
1,200 bushel corn.
But understand that it's a mechanical process that can go wrong, and just by virtue of how it's built, it can give you that wrong data. You need to go through and clean it, straighten it out, and get rid of that stuff, and then you'll have far better files in the future to work with. What time you got?
10-2. Let me see if
It's coming this way.
Oh, okay.
What's that?
It's coming.
Yeah. I greatly appreciate the time you guys have spent with us. I thank you, and I hope there's been a worthwhile couple days for you.
Thank you.
It's been a lot of fun for us.